NASA has already reached Jupiter. One probe hit its atmosphere at 106,000 miles per hour, fast enough to cross from Los Angeles to New York in about 90 seconds. It survived for less than an hour and vanished without ever reaching the ground. Because at Jupiter, the hardest part is not getting there. It is finding a place where arrival is even possible. Mars behaves like a destination. A spacecraft travels for months, slows down, finds a patch of ground that does not look completely suicidal, and lands. The Moon does the same. Even Venus, which treats machines about as gently as a blast furnace treats a plastic lawn chair, still has rocks. Soviet landers reached those rocks, sent pictures, and died while standing on something solid. Jupiter does not offer that courtesy. In December of 1995, a small probe from the Galileo mission separated from the main spacecraft and headed directly into the clouds. It was about the size of a large suitcase. It carried no crew, no food, no drinking water, and no plan to come home. Every pound was devoted to instruments, communications, a parachute, and a heat shield. Engineers removed almost everything that makes human travel difficult, including the human. The probe entered at about 106,000 miles per hour. At that speed, the atmosphere did not move politely out of the way. Gas piled up in front of the shield, compressed, and became a glowing layer of plasma. Temperatures in that shock layer climbed to roughly 28,000 degrees Fahrenheit. The visible surface of the sun is much cooler. Then came the braking force. The probe endured more than 200 times the pull of gravity on Earth. A 200-pound person would briefly feel as if tens of thousands of pounds had been stacked on the body. There would be no heroic final sentence. There would barely be time for the nervous system to understand that the trip had become a paperwork problem for somebody else. The machine survived. The parachute opened. Instruments measured wind, pressure, temperature, lightning, and the chemical mixture of the atmosphere. The heat shield had started the descent at more than 300 pounds. By the time its job was finished, more than half of that mass had burned away and carried heat with it. It did not crack off in convenient pieces. It became gas. For 58 minutes, humanity received information from inside Jupiter. Then the signal stopped. The probe had descended only about 100 miles below the visible cloud tops. On Jupiter, that is not deep. It is a scratch in the paint, except the paint is hundreds of miles thick and there is no wall underneath it. Pressure and temperature kept rising. The electronics failed. The structure was crushed, melted, and eventually vaporized. No wreckage reached a floor because there was no floor to reach. That was the deepest direct entry humanity has ever made into Jupiter. Less than 1 hour from a machine designed for one job, built without passengers, and sent on a mission where survival was never part of the contract. The obvious question sounds almost childish. Where is the surface? There is no surface. Jupiter is made mostly of hydrogen and helium. High in the atmosphere, those materials are thin gases. Farther down, the gas becomes denser. Deeper still, it behaves more like a fluid. There is no clean border where the sky ends and the planet begins. No shoreline, no crust, no moment when landing gear can come down and the flight computer can announce that the trip is over. Imagine diving into a swimming pool where the water changes with every foot. At first, it feels like mist, then like normal water, then like motor oil, then like syrup left in a refrigerator. Keep going and the material becomes so dense that familiar words stop helping. Jupiter works like that, except the transition continues for tens of thousands of miles. A falling spacecraft would not strike the ground. It would sink. Drag would slow it. At some level, it might even become buoyant if its average density matched the material around it, but that would not be a landing. It would be a damaged metal container floating inside a planet, surrounded by violent winds, rising heat, and pressure that keeps increasing below. There is nowhere to plant a flag. Nowhere to park a rover, nowhere to bolt down a laboratory. Jupiter has more volume than any other planet in the solar system and not 1 square foot where a human can stand. The mission has no final mile. A sensible person might say that nobody needs to enter. Stay in orbit, look through the windows, collect samples from a safe distance, and return home. That is exactly how robotic missions operate. The problem is that Jupiter starts attacking a spacecraft before the clouds are close enough to fill the windshield. The space around Jupiter is soaked in radiation. The magnetic field of Earth protects us from much of the charged material flowing from the Sun. It bends particles away and traps some of them in the Van Allen belts. That quiet protection is why a person can walk to a pickup truck in the morning without wearing a lead suit. The magnetic system of Jupiter is much larger and far more violent. It captures charged particles, traps them, and accelerates them to extreme speeds. The result is a set of radiation belts that can be roughly 20,000 times harsher than the belts surrounding Earth. This is not a beam that a pilot can dodge. It is an environment. Trying to steer around it would be like trying to avoid water while already sitting at the bottom of a lake. The Juno spacecraft, managed for NASA by the Jet Propulsion Laboratory, has been studying Jupiter since 2016. Its most important electronics are hidden inside a titanium vault weighing about 400 pounds. The vault protects the central computer and critical instruments, not the entire spacecraft. Engineers accepted that much of the machine would simply have to absorb damage, and it does. Every close pass adds radiation exposure. High-energy particles punch through materials, knock electrons loose, corrupt memory, weaken components, and slowly turn a sophisticated spacecraft into a collection of parts with an expiration date. Juno has continued returning data into 2026, but each orbit still adds another dose. Physics does not care how many committees approved the budget. A human spacecraft could add water tanks, metal shielding, and specialized materials around the living area. That sounds manageable until the shield has to be launched from Earth. Every extra pound requires more rocket. More rocket requires more fuel. More fuel requires a larger vehicle. The larger vehicle needs more structure, which adds more pounds, which requires more rocket. Spaceflight solves one problem by filling out the application for the next one. Near the most dangerous regions, an unprotected crew would receive an unacceptable dose before the real descent began. The Moon Io orbits inside an especially severe zone. Europa also moves through punishing radiation. Even NASA Europa Clipper will not sit beside Europa and calmly work like a weather satellite over Kansas. It will make repeated fast passes, gather data, and retreat along a long orbit that limits exposure. Jupiter is effectively saying, you may approach, but you may not remain. Suppose that problem is solved. Imagine a spacecraft with shielding far beyond anything available today. It survives the trip, enters the atmosphere, and begins to descend. Jupiter reaches for the next tool, pressure. The atmosphere of Earth presses on every square inch of the body with a force of roughly 15 pounds. We do not notice because pressure inside the body pushes back. On Jupiter, every mile downward adds the weight of more gas above. Soon, the spacecraft is not carrying a thin atmosphere over its roof. It is carrying a growing fraction of a planet. At depths of thousands of miles, pressure rises to millions of times the pressure at sea level. At that point, the question is no longer whether the hull is made of strong steel or stronger steel. Strength matters only while a material remains the material engineers designed. Deep inside Jupiter, pressure begins changing the electronic structure of matter itself. Hydrogen normally consists of atoms with one proton and one electron. Under ordinary conditions, electrons stay associated with individual atoms or molecules. Crush hydrogen hard enough, and those electrons can no longer remain politely assigned to one place. They move through the material. That makes the hydrogen conduct electricity like a metal. The result is metallic hydrogen. It is still hydrogen. It may still be fluid. But electrically, it behaves more like copper than like the gas used in a high school balloon experiment. Inside Jupiter, this conducting fluid probably forms an ocean thousands of miles thick. Nothing like that exists naturally on the surface of Earth. For decades, physicists tried to create metallic hydrogen in laboratories by squeezing tiny samples between the tips of diamonds. Diamonds are used because almost everything else gives up sooner. Even the diamonds sometimes decide that graduate school has lasted long enough and explode. In 2017, Harvard physicist Isaac Silveira and researcher Ranga Dias announced that they had produced metallic hydrogen at pressures approaching 5 million atmospheres. The sample changed from transparent to dark, then appeared shiny and reflective like a metal. It was microscopic, far thinner than a human hair. Other physicists were not convinced. The shine might have come from parts of the apparatus. The pressure measurement was disputed. The result had not been reproduced. Silveira planned additional tests, but the diamond anvils cracked. The tiny sample disappeared among the fragments. One possible piece of metallic hydrogen, after decades of work, was gone. Later experiments produced stronger spectroscopic evidence that hydrogen really does cross into a metallic state under extreme pressure. The basic physics is no longer a wild guess, but creating it, measuring it, and keeping it long enough for everybody to agree remains brutally difficult. On Jupiter, a layer of this material has existed for about 4.5 billion years. No diamonds, no vacuum table, no clean room, no research grant. The planet simply squeezes itself hard enough to manufacture an ocean that the best laboratories on Earth can barely imitate for moments. That ocean is moving. Jupiter rotates once in just under 10 hours. Earth takes 24 hours, even though Jupiter is about 11 times wider. The giant spins so fast that its equator bulges outward and its poles flatten. Data from Juno, published in 2026, forced scientists to refine the official dimensions again. The planet appears about 5 miles narrower at the equator and roughly 15 miles more flattened at the poles than older measurements suggested. 5 miles sounds small until the object being measured could swallow more than 1,300 Earths by volume. Jupiter is also about 2.5 times more massive than all the other planets in the solar system combined. The United States has studied it with Pioneer, Voyager, Galileo, and Juno, yet in 2026, we are still correcting the outline. The moving metallic hydrogen carries electric current. The electric current creates a magnetic field. The field interacts with the moving conductor and the entire system reinforces itself. This is a planetary dynamo, the same general mechanism that helps create the magnetic field of Earth, but built on a scale that makes our core look like a starter motor beside a hydroelectric dam. That dynamo creates the magnetic system that builds the radiation belts outside. The deeper mechanism produces the outer barrier. Jupiter manufactures its own security system. Below the metallic hydrogen, the old diagrams used to show something simple: a compact core of rock, metal, and ice. The core formed first, gas collected around it, and the planet grew layer by layer. It was clean, logical, and easy to print in a textbook. Juno ruined the drawing. The spacecraft moves along a long oval orbit and repeatedly dives close to the clouds. As it passes, gravity from different parts of Jupiter changes its speed by tiny amounts. Engineers measure those changes through radio signals. The method is like lifting a closed toolbox and shifting it from side to side. Without opening the box, a person can still tell whether the heavy wrench is packed in one corner or spread among the rest of the tools. The gravity data did not point to a neat hard ball in the middle. They pointed to a large fuzzy region where heavy elements are mixed with hydrogen. The boundary is not sharp. A smaller compact core may still exist, but the simple picture of a rock sitting inside a clean shell no longer works. It is less like a peach with a pit and more like somebody ground the pit into powder and mixed it through the fruit. Nobody knows exactly why. Maybe an early compact core partly dissolved into hot hydrogen. Maybe another large planetary embryo struck the young Jupiter and stirred the interior. Maybe the planet formed by a process that current models still do not capture correctly. The largest planet in the solar system has no visible surface and no agreed map of its center. People noticed that Jupiter felt different long before spacecraft existed. Babylonian skywatchers associated it with Marduk, the ruling god who defeated chaos and became king of the gods. Some ancient texts use the word Nibiru for a crossing point or celestial marker, and sometimes connected it with Jupiter and Marduk. Much later, writer Zecharia Sitchin reinterpreted Nibiru as a hidden planet returning every 3,600 years, home to the Anunnaki, who supposedly engineered humans to mine gold. Specialists in ancient Mesopotamian languages rejected his translations. The books sold anyway. That pattern keeps repeating. Jupiter becomes the king of gods, the home of visitors, the guardian of Earth, or the star that almost switched on. People have trouble accepting it as an ordinary planet because it does not behave like one in the ordinary sense. The most popular modern label is failed star. The idea sounds reasonable. The Sun is mostly hydrogen and helium. Jupiter is mostly hydrogen and helium. The Sun makes energy. Jupiter releases internal heat. Therefore, Jupiter must be a small star that missed the final step. The missing step weighs about 79 additional Jupiters. To begin normal hydrogen fusion, an object needs roughly 75 to 80 times the mass of Jupiter. Not 80% more, about 80 times the total mass. Calling Jupiter almost a star is like calling a 200-pound man almost a loaded tractor trailer because both contain iron and can roll downhill under the right circumstances. There is a middle category called brown dwarfs. Some can fuse deuterium, a heavy form of hydrogen, for a limited time. That range begins near 13 Jupiter masses. Our Jupiter does not even reach the entrance to that club. It resembles the Sun in composition because both formed from the same cloud. Two objects made from the same steel can become a kitchen knife and a bridge beam. The material does not decide the job. Jupiter does release more energy than it receives from sunlight, but no fusion reactor is burning inside. The planet is slowly shrinking under its own gravity. As material settles inward, gravitational energy becomes heat. This process has continued for billions of years. Weather on Earth depends heavily on sunlight. The Sun heats land and water, the surface heats air, and that energy drives much of the atmosphere. Jupiter receives energy from above and from below. Its interior helps power storms that can keep going without anything like a warm Gulf of Mexico underneath. The Great Red Spot is the most famous example. A similar reddish feature was seen through early telescopes in the 17th century, although nobody can prove it was the same storm. The modern spot has been observed continuously since the 19th century. It was already turning before electric power grids, commercial aviation, interstate highways, and cable news. Generations of Americans lived entire lives while one storm on Jupiter kept circling. The visible oval is still wider than Earth. Winds move at hundreds of miles per hour. Juno measurements show that the storm extends hundreds of miles below the cloud tops. The part seen in photographs is only the roof of a structure rooted deep in the atmosphere, and the storm is shrinking. It used to be much larger. Hubble observations over a 90-day period showed that the spot does not simply get smaller in a smooth way. It stretches, compresses, speeds up, slows down, and changes shape. NASA researchers compared it to a stress ball being squeezed in a hand. Nobody predicted that a storm larger than Earth would wobble like something bought beside the checkout lane at a pharmacy. On Earth, a hurricane weakens when it crosses land. Friction rises, warm ocean water disappears, and the storm loses its fuel. The Great Red Spot cannot make landfall because Jupiter has no land. There is no continent waiting to break it apart. The weather is not happening over the planet. The weather is part of the planet. At this point, the idea of a human expedition begins to collapse in every direction. A ship cannot land. It cannot remain close for long without enormous shielding. It cannot descend deeply without being crushed and heated. It cannot aim for a sharp, solid core because no such boundary has been found. Even the stripes and clouds that look like a surface are the upper skin of motions reaching thousands of miles downward. That still did not stop people from imagining that Jupiter could be turned into something more useful. In 1991, American author William Cooper published Behold a Pale Horse. Cooper had served in the United States Navy and later became one of the most influential figures in American conspiracy culture. He claimed that a secret plan called Project Lucifer would use the Galileo spacecraft to ignite Jupiter and create a second sun. The story had everything required for a long life. Galileo carried plutonium. NASA eventually sent Galileo into Jupiter. The collision was deliberate. All three statements were true. The conclusion was not. The plutonium was inside radioisotope generators. These devices use heat from radioactive decay to make electricity. They are not nuclear bombs. They do not produce the kind of explosion needed for a fusion reaction, and even a real nuclear weapon would not solve the actual problem. Jupiter does not need a spark. Jupiter needs dozens of additional Jupiters. A similar idea appeared in Arthur C. Clarke fiction, where Jupiter becomes a new star. Clarke presented it as fiction. Cooper presented a secret program. The Galileo orbiter worked around Jupiter for nearly 8 years. By 2003, fuel for controlling the spacecraft was running low. NASA engineers feared that a dead and uncontrollable Galileo might eventually strike Europa. Europa probably contains a global ocean beneath its ice. The spacecraft had been built on Earth and could carry hardy microbes. Nobody wanted to contaminate a possible habitat before future missions could study it. So NASA aimed Galileo into Jupiter on purpose. The orbiter disappeared on September 21, 2003. No second sun appeared. The planet did not flicker. Its atmosphere absorbed the spacecraft with less drama than a bug hitting a windshield on Interstate 10. The conspiracy survived because the underlying misunderstanding survived. Jupiter looks like a star that almost happened. It is huge, made of star material, warm inside, and powerful enough to move the sun. That last part is literal. The sun and Jupiter orbit a shared center of mass. Because Jupiter is so massive, that point can lie just outside the visible surface of the sun. The sun does not sit perfectly still while Jupiter circles it. Both bodies move around a point between them. Every other planet matters. Jupiter matters enough to make the sun wobble. Its gravity may also have rearranged the entire early solar system. One major scientific model is called the Grand Tack. In this scenario, Jupiter formed early and began migrating inward through the disk of gas and debris surrounding the young sun. It may have moved close to the region where Mars now travels. Later, Saturn formed, the two giants entered a gravitational relationship, and their migration reversed. Jupiter moved outward again toward its present orbit. The name comes from sailing. A boat approaches a point, changes direction, and heads away on a new course. Jupiter may have performed that maneuver with planets and asteroids instead of water and wind. The model helps explain why Mars is so small. Older simulations often produced a Mars closer to the mass of Earth. If Jupiter moved through that region and removed much of the available building material, Mars would have been left with an empty construction site. The model also helps explain why the asteroid belt contains bodies formed under very different temperatures. A migrating Jupiter could scatter rocky and icy material, mix the belt, and then leave it behind. A more dramatic hypothesis goes further. Before Mercury, Venus, Earth, and Mars formed, the inner solar system may have contained an earlier generation of large rocky planets. As Jupiter moved inward, its gravity could have destabilized them. Collisions would create debris. Gas drag would pull that debris toward the sun. The first set of inner planets could have been destroyed before Earth existed. There is no direct proof that those worlds were real. No telescope watched them fall. No surviving chunk carries a label from the previous neighborhood. The idea remains a hypothesis, and many researchers dispute the required details. But if it is correct, Earth was built from material left after Jupiter cleared the first development. The planet we cannot land on may have helped decide whether there would be ground beneath our feet at all. This leads to the most comforting statement about Jupiter. It protects Earth. The giant can capture comets, alter their paths, and throw some objects out of the solar system. It is especially effective against certain long-period comets arriving from the distant Oort cloud. That much is real. The problem is that gravity does not work for the Department of Homeland Security. It has no list of approved and unapproved rocks. The same pull can drag objects inward, change asteroid orbits, and turn distant icy bodies into short-period comets that repeatedly cross the inner solar system. Jupiter can remove a threat. It can also manufacture a new one. In the 1990s, American planetary scientist George Wetherill helped popularize the idea that a Jupiter-like planet protects habitable worlds. Later, Researchers Jonty Horner and Barry Jones ran simulations under the title Jupiter, Friend or Foe. They changed the mass of the giant and tracked what happened to different populations of asteroids and comets. The answer depended on which objects were counted. For some long-period comets, a massive Jupiter reduced danger. For other comets and asteroids, its gravity increased the number entering Earth-crossing paths. Other studies still support an overall protective role under certain conditions. The argument remains open because nobody has a spare solar system for a controlled experiment. Jupiter is not simply a shield, it is a gravitational traffic controller with no concern for who owns the windshield. And then comes the final contradiction. The planet itself may be impossible to enter, but one of the best places to search for life circles beside it. Europa is slightly smaller than the Moon. Its surface is bright ice crossed by long dark fractures. It is one of the smoothest large bodies in the solar system. There are few tall mountains and relatively few old craters. The surface appears to be renewed as material moves and refreezes. Below the ice lies a global ocean. That ocean may contain roughly twice as much water as all oceans on Earth combined. Sunlight at the orbit of Jupiter is too weak to keep it liquid. The heat comes mainly from tidal flexing. The orbit of Europa is slightly stretched rather than perfectly circular. As the Moon moves, the gravity of Jupiter pulls harder and softer at different points. Europa is squeezed and relaxed over and over. Internal material bends, rubs, and produces heat. Bend a metal coat hanger back and forth, and the bend warms. Now replace the coat hanger with a moon and the hand with Jupiter. The same gravity that may have scattered planets keeps an ocean liquid in darkness. The same magnetic environment that damages spacecraft also makes that ocean difficult to study. NASA launched Europa Clipper on October 14, 2024. The spacecraft will travel about 1.8 billion miles and is expected to reach Jupiter in April of 2030. It will not land. It will not drill through the ice. It will make 49 close flybys, map the surface, examine the ice shell, search for signs of water movement, and measure conditions that could support life. Its electronics are protected inside a radiation vault because Jupiter does not make exceptions for missions carrying the NASA logo. The European JUICE mission is also on the way and is expected to arrive in 2031. It will study several icy moons, especially Ganymede. Humanity is returning to the Jupiter system, not because the planet became safer, but because the moons beside it became too important to ignore. On Earth, wherever liquid water, chemistry, and energy exist together, life finds ways to occupy places that look impossible. Boiling springs, acidic lakes, deep rock, dark ocean vents, under Antarctic ice. Nobody knows what is inside the ocean of Europa. That is not a dramatic phrase. It is the current scientific answer. Humans can reach the Jupiter system. We have done it repeatedly. Pioneer passed by. Voyager passed by. Galileo entered orbit. Juno is still returning data. Europa Clipper and JUICE are on the way. The distance can be crossed. The planet cannot be completed as a journey. Radiation attacks before arrival. The atmosphere offers no ground. Heat consumes the shield. Pressure changes the state of matter. Hydrogen becomes a conducting ocean. The core dissolves into a fuzzy region. Every new layer removes another familiar word. Surface no longer works. Landing no longer works. Center barely works. Even planet begins to feel too simple. A wall would be easier. A wall can be drilled, climbed, broken, or circled. Jupiter is not closed by a wall. It is closed by a continuous transition from one lethal condition into another. A spacecraft can follow the correct course for hundreds of millions of miles. It can arrive at the exact coordinates. It can enter the clouds within seconds of the planned time. The mission can be perfect. And still, there is no moment when the traveler has reached Jupiter in the way a traveler reaches Mars, the Moon, or Earth. There is only deeper. NASA has already proved that we can get there. Galileo proved something harder. At Jupiter, reaching the destination and arriving are not the same thing.